Good afternoon, everyone. Thank you for coming to my talk. And thanks, Laura, for the introduction. And my name is Ziaozhou Ma, and now I'm a postdoc in Catalysis Engineering Group, working with Professor Monique van de Veen. And today I will talk about my PhD work that is using Redox-Active pi bridging ligand as a control switch of intramolecular magnetic interactions. So we are all creating data every day. So it is said that the data creation will grow to an enormous of 175 zettabytes by the year 2025, meaning that there are more and more data that will be needed to be stored. And currently the hard disk drive, I will change to the PowerPoint. Okay, the hard disk drive remains the dominant storage technology in the data center, and the core part of the hard disk drive is the magnetic material that's used for storing information. So since we amass more and more data nowadays, so there is a growing need for the development of new material with high information storage ability. The molecule-based nanomagnets can be promising candidates because this type of material, they show similar bistability or hysteresis compared with bulk magnet. This is the first example of a single molecule that shows magnetic memory in fact. So imagine that if a single molecule could be used to encode a binary data, then a vast increase of the information storage ability could be achieved. And these molecule-based nanomagnets, such as single molecule magnet or single chain magnet, they are zero-dimensional discrete molecules or one-dimensional molecular chain that are made of paramagnetic metal ions or inorganic or organic ligands. Therefore, the magnetic properties of the material can be somehow controlled or enhanced by a suitable choice of the molecular components. Meanwhile, since the magnetic properties usually comes from the cooperative effects between the spin carriers, so the choice of the linker is therefore crucial because it mediates the magnetic interaction between the spin carriers. And importantly, this magnetic interaction is an essential parameter for the design of high-performance molecule-based nanomagnets. The majority of the single molecule magnet or single chain magnet, they are made of paramagnetic metal ions connected by a diamagnetic bridging ligand through a super exchange pathway. Usually it is very weak. So in order to increase the magnetic interactions, one efficient approach is called a post-synthetic method using a redox-active ligand. And there are two steps involved in this post-synthetic method. First, in the first step, a coordination complex is synthesized using a paramagnetic metal ion and a diamagnetic redox-active ligand. Then redox chemistry can be conducted on this compound to oxidize or reduce the ligand into radical form, which could act as a magnetic relay between the spin carriers and enhancing the magnetic interactions. Meanwhile, since this redox-active ligand, it can undergo reversible redox processes. Applying them into the molecule-based magnets could also provide multi-switchability and allow a certain tuning of the magnetic interactions. This post-synthetic method has proved to be robust, with few reported examples shown here. In this dinuclear compound, by reduce once the ligand, when it becomes radical form, an enhancement of the magnetic interactions has been achieved between the metal ions and the radical ligand. Meanwhile, this reduced compound also shows slow relaxation of magnetization from this AC magnetic susceptibility measurements, meaning that it becomes a single molecule magnet. Meanwhile, incorporate this redox-active ligand into one-dimensional molecular chain can also give rise molecular chains that shows redox switching abilities. In these manganese systems, by reducing once the bridging ligand, a great enhancement of the magnetic coupling strength has been achieved. However, with very few reported examples, this post-synthetic method remains challenged. Therefore, it also motivates us to work on highly coupled systems based on the redox-active ligand. So in our request to design an ideal redox-active ligand, this tpha ligand is selected because first, it is reported to be redox-active, but it has never been used in any magnetically interesting material. Meanwhile, we can see its strong complexing ability thanks to this bis-tridentate coordination mode, and together with its planarity and the rigidity of the ligand, should force a formation of the short metal-nitrogen bond, which could increase the magnetic interactions between the spin carriers. Meanwhile, this feature, together with the pi systems of the ligand, which could also support a large electron delocalization through the systems when the ligand is reduced into the radical form. Therefore, in my work, I use this tpha ligand to connect the open share transition metal ions to build a dinuclear systems as a prototype. So today I will only focus on the work based on the chromium-3, cobalt-2, or nickel-2 as metal centers. And in this dinuclear compound, terpridine was chosen as a capping ligand in order to fulfill the coordination mode of the metal ions. And with these dinuclear systems, we can first investigate the redox activity of both ligand and the metal ions, as well as the radical ligand, the role of the radical ligand in influencing the magnetic properties. Meanwhile, with these systems, it's important for us to understand the relationship between molecular structures and the magnetic properties. Once the highly coupled systems is selected by our study, it can further be used as building blocks or magnetic units to build higher nuclearity or extended systems, which will act as efficient molecule-based nanomagnets to meet the requirement of high information storage. Therefore, in the first part of my work, I synthesized the cobalt dinuclear compound based on the synthetic method shown here, and the final product was characterized by single crystal X-ray diffraction, which confirms the expected structure with two crystallographically equivalent terpridine cobalt coordinated by a 1x1 tpha ligand. And since I have both redox-active metal ions and the ligand in my complex, the first thing to do is to investigate its redox activity. And the cyclic photometry measurement is shown here. And since the rise potential is close to 0, all the 4 peaks are belonging to the reduction processes. And since the first 3 peaks are very well separated, showing that the once and twice reduced compound could be stabilized. But with only the spectra shown here, we cannot just attribute all these peaks. So in order to further investigate this cyclic photometry measurement and to attribute all the peaks, I used this not reduced compound as a starting material to react it with one equivalent or two equivalent or strongly reducing agent KC8. I obtained this once, twice, or even 4 times reduced complexes. And the successful of the reduction processes is first confirmed by charge balance, which we can see here. And the reversibility of the redox processes is also checked by oxidizing the once and twice reduced compound using silver PF6. So the bond distance first is a good indication of the oxidation of spin states of the metal ions. Then the cobalt and nitrogen distance between here, these two cobalt nitrogen 1 and cobalt nitrogen 3 is quite large due to the rigidity of the ligand. So in order to determine the oxidation state of the metal center, it's more meaningful to look at the cobalt nitrogen distance between cobalt and terpyridine. So by looking at all these values, we see that in the not reduced and 4 times reduced cobalt compound, the cobalt center is in their low spin state, while for once and twice reduced complexes, the cobalt-2 center are in their high spin states. This assumption is further confirmed by theoretical calculations, which we collaborate with Dr. Elizaveta Sturina from University of Bath. So according to this ligand field splitting of 3D orbitals, we can see that for the not reduced and 4 times reduced compound, the cobalt center is indeed in their low spin state, while for the once and twice reduced compounds, their cobalt center are in their high spin state. And the oxidation state of the cobalt center actually didn't change in these 4 complexes. They are all in +2 oxidation state. And since the oxidation state of the cobalt center didn't change, the reduction processes we talked before are all centered on the ligand. So we see that these 2 reduction processes are actually centered on the pyrazine ring of the bridging ligand, because there is a significant elongation of this nitrogen-nitrogen distance on the pyrazine ring of the ligand, and also an increase of the carbon-nitrogen distance upon reduction processes. And the bond distance in terpyridine didn't change much upon the 2 reduction processes, but for this 4 times reduced compound, the bond length in terpyridine has a significant change. So we assign these 2 peaks comes from the reduction of terpyridine. Now we can see that these 2 peaks comes from the reduction of the tpha ligand, and the other 2 comes from the reduction of terpyridine. Since I have different complexes in different oxidation states, the most important thing to do is to investigate its magnetic properties. And for this not reduced cobalt compound, all my magnetic properties was evaluated according to the different magnetic data and by fitting all this data using different models. I will not go into detail about the analysis procedure, but to focus on some key informations we got after the analysis. So for this not reduced cobalt compound, we can see that above 200 K, it undergoes a spin crossover phenomenon, meaning that the cobalt-2 low spin is changing to cobalt-2 high spin with the increasing of temperature in this complex. And below 200 K, it shows a small antiferromagnetic exchange coupling between the two cobalt to low spin centers with a G value equals minus 12.7 K. So when reduced once the bridging ligand, for this once reduced cobalt compound, a large antiferromagnetic exchange coupling is observed between the and the radical ligand. So we can see that the magnetic interaction is indeed increased by reducing the ligand into their radical form. Meanwhile, this compound also shows a slow relaxation of the magnetization from the AC magnetic susceptibility measurements. So it is a single molecule magnet. So by reducing once the bridging ligand, we are able to tune the magnetic properties from spin crossover to single molecule magnet. What will happen to the twice reduced compound? In this twice reduced compound, actually we are putting 2 electrons on the center bridging ligand. And with paired electron on this ligand, it becomes diamagnetic again. So in the beginning, I'm expecting a small exchange coupling between the spin carriers. However, according to the thermal behavior of the Ct product shown here, there is a very strong antiferromagnetic exchange coupling between the two cobalt-2 high spin centers. And this value, which is minus 74 K, is much stronger than the expected value, with two cobalt-2 high spin centers bridged by a diamagnetic ligand. This result is quite surprising, and this surprisingly large antiferromagnetic exchange coupling could be explained by the orbital considerations. Because in this twice reduced compound, if we look at the ligand field splitting of 3D orbitals of cobalt, we see that the unpaired electron is located on dxy, dz square, and dx square minus y square orbitals. While for this dx square minus y square and dz square orbital, it interacts weakly with the sigma orbitals of nitrogen on the ligand. For this dxy orbital, it actually interacts strongly with the pi orbitals of the ligand, which provide a channel for a large spin delocalization through the systems. Therefore, we observe a large antiferromagnetic exchange interactions. So from this part of work, we learned that the redox-active ligand can really have an important influence in tuning the magnetic interactions, and a large antiferromagnetic coupling has been promoted in this once and twice reduced compound due to the singly occupied dxy orbital that it overlaps with the pi systems of the bridging ligand that the electron could delocalize through the systems. So in order to further investigate the role of this d orbital in influencing the magnetic interactions, we decided to change the electron configurations of the metal centers. We are going to put one more electron on the metal ions. So the nickel-2-based analogues was synthesized, which used the similar synthetic method like I did with cobalt. And also the cyclic wattmetry measurements shows that this compound is redox-active, with 2 peaks come from the reduction of tpha, and the other 2 come from the reduction of terpyridine. And based on this, I used the not reduced nickel compound to react with 1 equivalent or 2 equivalent of strongly reducing agent KC8. I obtained after recrystallization the once and twice reduced complexes. The oxidation state of the metal centers is also checked by the bond lengths, and the nickel and nitrogen distance between nickel and terpyridine which are shown here, didn't change much on these three complexes, indicates that the nickel 2 are in their +2 oxidation state in these three complexes. Well, if we see the carbon-nitrogen distance and the nitrogen-nitrogen distance here on the pyrazine ring of this tphc ligand, we can see a significant increase of the values, meaning that the two reduction processes is actually centered on the ligands. So the only difference between the cobalt series and the nickel series complexes is the electronic configurations of the metal centers. So by comparing the magnetic properties between cobalt or nickel complexes, we could have an idea of the role of the DXY orbital in modulating the magnetic interaction. So we can start from this twice reduced nickel compound. The magnetic data shows that there is almost no interaction between the two nickel 2 spins, which is in marked contrast to the twice reduced cobalt compound that we observed a very strong antiferromagnetic exchange coupling between the two cobalt 2 high spin centers. So according to this ligand field splitting of 3D orbitals, we can see that in nickel metal centers, this DXY orbital is really fully occupied. So the unpaired electrons, which are located on dz square and dx square minus y square orbital, it interacts weakly with the sigma orbitals of nitrogen on the bridging ligand. So the spin densities are mainly located on the nickel metal centers. Therefore, the magnetic interactions is necessarily to be weak. And as for this once reduced nickel compound, the magnetic behavior shows that there are ferromagnetic interactions between the nickel spins and the radical spins. This ferromagnetic interaction actually is due to the orthogonality of the singly occupied d orbital and the thermal of the bridging ligand. And by comparing with the once reduced cobalt compound, which we know that they have a large antiferromagnetic interaction between the cobalt 2 high spin center and the radical ligand, we can see that the magnetic interaction, which promoted by singly occupied dxy orbital and the thermal of the bridging ligand, is really large, which can overcome the ferromagnetic interactions that promoted by the orthogonality of the singly occupied d orbital and the pi systems of the ligand. So by roughly estimation, we can see that this value is at least minus 700 K. Still, this ferromagnetic interaction, the value shown here is quite large than the reported ones between the nickel spin and the radical ligand. So by reducing once the bridging ligand, we can still promote a large magnetic interactions. And the not reduced nickel compound, there are very small interactions between two nickel 2 spins. So from all above experimental or theoretical studies, we know that this dxy orbital in the systems overlaps the best with the pi systems of the bridging ligand. So if we have a singly unpaired electron on this dxy orbital, it will interact strongly with the pi system of the ligand. So it will promote a large magnetic interactions. So to continue our work to build highly coupled systems, the chromium-3 metal ion with D3 electronic configuration was chosen because in chromium-3, all T2G orbital are singly occupied. So the presence of singly occupied dxy orbital can be guaranteed. And meanwhile, with empty EG orbitals, we will not observe any ferromagnetic contributions that has been seen in cobalt or nickel systems. So in the beginning, I want to build the dinuclear chromium systems like I did in cobalt or nickel series. But with many trials, I didn't succeed to obtain the dinuclear compound. I only obtained a mononuclear chromium compound. So we reason that once one side of this ligand is coordinated to the chromium, it is withdrawing electron density from the ligand. So it's hard to put another one on the other side. And meanwhile, this nitrogen-nitrogen distance becomes very large. So actually, it no longer fits a metal ion with small ratios like chromium-3. But still, it's interesting to investigate this mononuclear complex because first it's redox-active. So if we could have the complex with radical tpha ligand, we can also investigate the magnetic interactions and to complete our work based on the nickel and cobalt systems. Therefore, I use these two as starting material to react with one equivalent of two equivalent of a moderate reducing agent cobalt-thin. I obtained the once and twice reduced chromium complexes. And from the bond distance, this value of the not reduced chromium compound is consistent with the reported ones with one chromium-3 coordinated to two neutral ligands. As for this once reduced compound, we can see a significant change of this nitrogen-nitrogen distance on the piercing ring of the tpha ligand. So we think that in this complex, the tpha ligand is reduced into radical form. And as for this twice reduced chromium compound, we not only observe a increase of the nitrogen-nitrogen distance, but also a decrease of this carbon-carbon distance on terpridine. So we think that in this complex, not only tpha is reduced into radical form, and also terpridine is reduced into its radical form. And the magnetic properties of the not reduced compound shown here is consistent with a mononuclear compound with a single chromium-3 spins. As for this once reduced chromium compound, the magnetic behavior shows a strong antiferromagnetic exchange coupling between the chromium-3 spin and the radical spins. For the twice reduced chromium complexes, we observed not only a very strong antiferromagnetic exchange coupling between the terpridine radical and chromium-3 spins, but also between the chromium-3 spins and the tpha radical. The data which we have between this temperature range preclude any exact quantification of the large J value by fitting the data. But from the DFT calculations, we have a rough idea of the exchange coupling between the spins and the radicals, which is estimated to be at least minus 1,500K. This is really huge, and the result is really exciting. And thanks to this dxy orbital in the chromium, singly occupied dxy orbital in chromium-3 metal ions, it overlaps with the pi systems of this tpha ligand. So a large magnetic interaction could be observed between the metal ion and the radical ligand. While for the twice reduced compound, this dyz orbital of chromium-3 is singly occupied, and it interacts strongly with the pi systems of terpridine. so that we could also observe a large magnetic interaction between the terpridine radical and the chromium-3 metal ions. So overall, the first part of my work shows that the redox-active ligand is really useful in promoting large magnetic interactions and also in tuning the magnetic properties in the dinuclear cobalt systems. And with the dinuclear nickel systems, a large ferromagnetic interactions is promoted. And meanwhile, by comparing with the cobalt systems, we see that this singly occupied dxy orbital, it interacts strongly with the pi systems of the bridging ligand, which provide a channel for large electron delocalization. For the chromium systems, we finally find the most highly coupled systems with a large J value at least minus 1,500 K. So these systems could be used as a magnetic unit or building blocks for the future design of high temperature magnet. So I believe my work shows some understandings of the factors that governs the magnetic interactions and can contribute to the future design of high temperature molecule-based nanomagnets. Okay, this is basic. Finally, I would like to thank all these people who contribute to all these works, and also thank you all for your attention.